Good morning. Welcome to FreeSlate's webinar on high-throughput chemicals and energy applications. My name is John Chan. I am the Communications Manager at FreeSlate. I will be your host for today's webinar. Today, you'll hear a presentation on the application of high-throughput research for heterogeneous catalysis. We're pleased to have Ms. Heather Brown from PNNL, Pacific Northwest National Laboratory, as our speaker today. We'll conclude today's webinar with a brief question and answer session at the end. Before we start, let me invite you to submit questions using the Q&A window on the right-hand side of your screen during the presentation. In the Q&A window, you can simply type in your question and press the submit button. Time permitting, we'll answer these questions at the end of the webinar. For any questions that we cannot get to, they'll be answered in follow-up emails. Our speaker today is Ms. Heather Brown. Ms. Brown is a research scientist at PNNL, Pacific Northwest National Laboratory. She joined PNNL's Chemical and Biological Process Development Group in December of 2005. Originally hired to maintain various analytical instruments, she now manages the combinatorial high-throughput laboratory. The combinatorial laboratory is a unique capability in PNNL which allows for the rapid screening of catalyst and reaction processes. The lab consists of several liquid handling robots designed for sample manipulation such as dilutions and derivatizations and catalyst preparation, multi-well batch screening reactors, a multi-channel flow reactor, and several analytical instruments. Ms. Brown utilizes her chemical, analytical, and programming experiences to coordinate workflows for a wide variety of projects, primarily in the field of biomass utilization. She and her team provide experimental design, execution, data processing, and reporting as part of the Combinatorial Service Center at PNNL. Her presentation today is titled Combinatorial Techniques for Heterogeneous Catalyst Screening. Heather?
Thanks, John. Good morning, everyone. I'm excited to be here today and look forward to discussing how we utilize our high throughput equipment, specifically for heterogeneous catalyst screening. On the next slide, I'll go over just a little bit of the key subject matter points that we are going to discuss today. So first of all, throughout the presentation, I'm going to be giving several examples of how we utilize our equipment and kind of examples on how to use some of these key points. So I'll do a brief overview of the experiment that I'll be talking about. From there, the basic points I would like to discuss with you today is, number one, how to design a good experiment. This is one of the key aspects of doing high throughput work, doing any really experimentation. And it's even more important with high throughput work since we're doing so many tests all at once. So that's the first thing I would like to discuss. The second is instrument validation. And some of the key things I'd like to discuss is the fact that you can modify your Automation Studio protocols. You can modify your deck on several of your robots. And you can even make alterations to some of the high throughput reactors. I've got several examples of how we've taken our experiments and our robotics and made changes to fit our needs. The third point I'd like to really stress today is the use of controls and replicates, because we're doing high throughput data and you need those to be able to ensure that your data is credible. So we'll go over some of the key points in that. And the last thing I'd like to discuss, as any of us know in high throughput work, there's a lot of data in the end. And so I'd like to give some pointers that we've learned here at PNNL along the way to facilitate analyzing that data. So let's get right into it with the next slide. The experiment I'll be talking about today goes over a 4-component catalyst optimization screening. we had a client come in that had a 4-component catalyst that they knew worked really well for the chemical process. They had done a lot of studies on this catalyst, and they knew some of the importance of the different active components on this catalyst. But that all takes time when you're doing one reaction at a time, one flow reaction. So they were hoping that our high throughput equipment could help determine their optimized metal loadings for this 4-component system, and also give some significance on what each of those components actually provided, be it high conversions or specific product yields, things like that. Unfortunately, through this presentation, I can't discuss the specific process that they were using. It is a conversion of biomass to fuels. But as far as specific details on that, I can't really discuss it due to client sensitivity. I also can't discuss a lot of what the catalyst actually is or what the components are. So I'll be referring to them as Catalyst X, and the different active sites on this catalyst as A, B, C, and D. And as we get further into it, you can kind of see where I'm going with that. We decided for this client that we would go ahead and design several factorial experiments based on this control catalyst. And our experimentation process would include automated catalyst preparation using an incipient wetness impregnation technique, which I will discuss a little bit later for those that aren't familiar with heterogeneous catalyst prep. And we followed this up with batch testing in our SPR reactor. Once we got most of that done, we went ahead and extended the run time in our batch tests for a lot of the top performing catalysts. And then finally, the plan is to finish the experimentation with larger scale flow reactor testing of the very top catalysts that we decided to look at a little bit closer, the ones that seem to be the best. Today, mainly, I will focus on the catalyst preparation and the batch testing because that is definitely more of a high throughput. The flow testing is much more standard. A lot of people are probably pretty accustomed to that. So that kind of gives you an overview of the experiment I'll be going over and going back to throughout this presentation. If you have questions on that, I'll try to answer those best I can. And so feel free to go ahead and put stuff in. So on the next slide, I'd like to talk about some of the key points in experimental design. As John mentioned, I manage the combinatorial service center here at the lab. And actually, one of the most important things I think we offer is experimental design. We have a core team that works on this equipment. And so when our clients and when the different project managers that I work with come to us and want to do an experiment, I have to spend a lot of time making sure that they understand that it takes time to design these experiments. So if you imagine, most people are really familiar with like a single reactor run or a single batch experiment. If you think about that, as scientists, we can spend days planning that experiment. So why in a high throughput setting where you could be looking at hundreds of cells, would you think you'd take less time to design that experiment? You actually should take more. So the thing that I like to stress to everyone the most is that putting in the time to properly design your experiment is really, really important because that's the only way you're going to get good data at the end. So what are the things you should look at? The number one first step is to determine your variables. That seems kind of obvious, but it's a good point just to sit down and really mark those out. And then from there, you can kind of determine how you plan to run. In a batch environment, we're running on a plate-by-plate basis. So the idea is, do you batch some of your variables? So one of your metal components, maybe it's kind of standard. Do you batch that and change that as you go from plate to plate? some of the other variables for catalyst preparation, for heterogeneous catalyst preparation, are often your support. That's another really good one to batch. You might have 6 different supports you're looking at with various metal components on them, and you can run one support per plate, basically. If batching doesn't come in very handy, the second best thing is to randomize your cells or your variables, and this usually ensures uniform testing. So those are some of the things to consider as far as determining your variables. The second step is definitely including proper controls in your tests. This can be really simple. I think a lot of times people put a little bit too much stress on choosing a proper control. Oftentimes, it is just a standard catalyst for us that the clients provided us. They know what this catalyst does, and the goal is just to have something on the plate, on every single plate that you run, that you can make a comparison to. And I'll kind of show you examples of why that's important a little bit later on. The next step is definitely considering replicates. You have to remember that in a high throughput environment, your data is all about statistics. You want to be able to run enough replicates that you can actually perform statistical calculations. Most people kind of settle on 3, but for a lot of statistics, 5 or 6 is actually preferable. So it's a balance, and I'll talk a little bit more about that later too. And finally, include in your design experiment process standards for your analytical process or your analysis up front. I don't know how many times we've run into going halfway through an experiment and going, oh, we should have done this type of analytical, and we just didn't think through that process. A lot of times we're so excited to start running that you kind of look over a lot of those things. So you want to make sure you look at this process, the design process, holistically, basically. So let's look at a few examples on the next slide. This is the design that we decided to utilize for our client. Like I mentioned before, we did a factorial design. And a factorial design is basically you take every single variable you have and you combine it with every other variable that you have. And for us, you define a certain number of levels. We were looking at 3 different levels for each of the 4 catalyst components, which when you combine all of those together, you get a total of 81 catalysts that we were planning on screening. The beauty of it is we could prep all these 81 catalysts all in one fell swoop on a 96-well plate using high throughput, whereas if somebody were to make this by hand, it would have taken a significantly longer amount of time. We also wanted to look at 0-level loadings. So instead of adding a 4th level to our 3 levels that we were planning on looking at, our low, medium, high, we decided to do just a second set of catalysts where we did a 2-level study with all 4 components, where one of the levels was 0, and then one of the levels was what we determined kind of an optimal loading from the 3 levels we looked at previously. And so that made a total of 16 additional catalysts. So that's sort of the factorial design we decided upon. As far as plate controls, we went ahead and did 3 of them. Control X, like I said, that was the catalyst that the client provided us. We knew it had high activity. It was sort of our marker, our goal for it. And then we also chose Control Y. This is actually the catalyst that they started with when they first started looking at this chemistry, and it had a lot lower activity. So that gave us a good range. And then we also did what I call a Combi Control X. This is the exact same composition as Control X that they provided us, except we prepared it robotically. And so what that does is it allows us to check both the reactivity differences, but also our preparation differences. As far as replicates go, we settled on 3 replicates per catalyst and 2 replicates per control. That kind of gave us the most bang for our buck, if you want to put it that way. We were running a 48-well plate, so we were able to run enough catalysts and still have enough replicates in order to do some statistics. And we felt confident enough with our controls that with 3 of them, if we had a couple that didn't work, we at least had something to compare. And finally, as far as initial analytical techniques, number 1, we used mass recovery as a first run through, and then carbon analysis was really important for us, and then followed that up by a simple liquid chromatography analysis. So that's sort of what we did as far as the design on the specific experiment. The next step in the process on the next slide is something I think a lot of people really overlook. I think as scientists, we are so excited to start something new and to get to screening and discover those new compositions as soon as possible that we just want to jump right in and start going. But I stress to my project managers and my clients that we need to make sure that the instruments are working for us, not against us. And so validation of the instruments, I think, is key. So the first step in validating is always defining what are the key points in your screening process. So is the kind of the linchpin going to be your catalyst prep, or is it going to be the reactor, or the reaction conditions? What really makes or breaks your screening process? And then you have to determine how the instruments either help or hinder, those points. So some of the things to remember, and the things I'm going to cover right now we did, is you can always modify your Automation Studio protocols. And robot deck configurations are definitely not set in stone. And even things such as your reactor plates that you're actually doing your chemistry in, those can be modified too. Just because that's the way the instrument comes doesn't mean that's the way you have to always run it. And I think a lot of people will take that for granted. I know I did when I first started, and when I started questioning stuff like that, we started getting better results and better results quicker without wasting time going backwards. So let's just go over some key examples. On the next slide, I wanted to give everybody just a real brief overview of heterogeneous catalyst prep, just in case people weren't familiar. I won't spend a whole lot of time. If you have questions on this, feel free to type them in now, and that way we don't forget about them as we go. But for heterogeneous catalyst prep, robotically, one of the easiest preps is incipient wetness impregnation. So you're utilizing the support's pore volume, how much liquid it can uptake, to add your usually metal active components as a liquid to that support, and after drying and activation, you get a final catalyst. So the step 1 in this is getting your supports added to your plates. Those are usually silicas, zirconias, carbons, aluminas, things like that. And on the deck here, you see there's a vibration table, and that's actually used to move the supports while you're doing the impregnation. The second step is, of course, we don't mix up all of if we're prepping 81 catalysts, we don't mix up all of the individual 81 metal solutions that are going to be added to those supports. So what we do instead is step 2, we use metal precursors and dissolve those into bulk solutions, basically. So you might have 5 different metal precursors on your deck as a substrate. And then robotically, using the liquid handling part of the robot can prepare the 81 different loadings of all those different metals in 81 different vials. And then those unique metal compositions in step 3 are then added slowly to the support while it's shaking. And like I said, then that's followed by calcination and reduction and activation, whatever your catalyst requires. So hopefully that makes sense to people if you're not familiar. So that was a key thing that we had to analyze, is that process of the actual catalyst prep to how well the instrument's working. And what we found out on the next slide is we needed to change our Automation Studio protocol. That was step one. What you see in the picture to the right is a support with a metal solution added to it. Both of them have had metal solutions added to them. The difference is that on the vial on the left, we added that metal solution as what I call a single slug. So the entire volume, the entire pore volume that we were adding to that support was added all at once. And during that time, the support was moving, but it was added all at once. On the vial to the right, we added it dropwise, so about 10 to 20 microliter additions were added. There was a wait period while the thing was shaking, and then another droplet was added until we got up to the pore volume. And as you can see, we saw a huge difference just by changing the way that the protocol was adding the amount we wanted to add. We got much better, slower absorption of the metal solution into the support pores. We ended up not coating the vial walls with our solution, which gave us better uniformity. We were able to do larger prep sizes. It just made a much more uniform catalyst. Because, of course, in the goal, one of the main goals anytime you're doing incipient wetness impregnation is your support should always be free-flowing, even when you're adding liquid to it. So that was number one, and we had to stop and say, okay, what can we change? So we changed the protocol. On the next slide, we actually made an additional modification to our deck. It was a minor modification, but it had huge impact. So on the pictures at the top, what I am trying to illustrate is the difference between stabilizing the vial, holding the support, versus not stabilizing the vial. The first one shows no stabilization. And what happens is as the vial is sitting on the shaker plate, we found that a lot of the vertical vibration was being transferred to moving the vial or causing the vial to jump, not moving the support specifically. So by actually holding down, so what you get is the little diagram on the right of that picture kind of shows the arrow up and down. You get a lot of metal solution on the top and it not really working into the support. If you actually hold down that vial, that helps, or stabilize the vial, that helps transfer all the vertical motion directly to the support. The vial becomes sort of non-existent at that point. And what you get is the little diagram to the left of that picture is a more of a churning motion where additions from the top, that support moves down and into the support and kind of unifies makes it more uniform addition in general. The picture at the very bottom kind of shows those vials jumping. So you can see the ones on the left aren't held in place, and the ones on the right are. And you can see the support is flying all over the place inside of those vials, which is why we were having such a hard time getting uniform additions. And this was, like I said, this was a very, very simple addition. It was the addition of a rubber sheet, basically, to our vials. But it was technically a deck modification, and doing this has caused us to reanalyze a lot of the different ways that our plates work and how they're located on the deck, so that we've changed other things. We've actually changed entire vertical shakers, for a specific type of support. So I've got lots of examples of that if you guys have questions on that. So the very last slide, the next one, where we did modifications to our instruments, had to do with modifying our SPR plate. And a lot of people will overlook the SPR reactor as something you can modify because it's a pressurized system and stuff. But the beauty actually of the SPR design with modifications in mind is that it's a shell with a reactor inside of it. And that reactor inside, that plate, can be changed as long as it fits inside. It can be changed without affecting your pressure ratings or your temperatures, as long as you use temperature-appropriate materials, of course. So for us, the reason we did this change is that catalyst coking for this specific experiment was really key. And the SPR, as many of you probably know, comes with metal vials. And we wanted to do visual inspection as kind of a first analytical yardstick to discard catalyst compositions. So we wanted to do something with glass, which means we actually modified our aluminum plate and so that it would accommodate glass vials. It was a very easy modification, but it made a huge difference. It also made things disposable, which personally I think we all like. It saves us time and in the long run. And the other small modification we made too was we used a Teflon sheet with pinholes in it between the graphite and vials. Usually, anybody familiar with this sort of design, the SPR design, it's a metal top plate with pinholes in it, followed by a graphite sheet with holes that go directly on the vials. And we found that the Teflon had added to limiting crosstalk and solvent loss in our system. So those are just three key things that we changed just for this optimization experiment. And like I said, they were just key points that we looked over and decided these were things that were hindering us from doing our work as best we could. And so we made modifications and did our validations, and things looked really good. So on the next slide, I just wanted to go over a few key points. As I said, controls and replicates are really important. And the main reason we do controls is so that we can actually compare the different batches or the different plates of testing. We found that plate-to-plate reproducibility is always a lot harder to accomplish than vial-to-vial along one plate. And I think that's just because there's a lot of variables that you can't control between plates. And so by putting in a control, you can know with confidence that the two plates can be compared. As I said earlier, consider using a high and a low activity control, because this allows you to monitor the entire range of the experiment. If you're only looking at a high activity control, you might be surprised that low activity, maybe for some reason your reactor heated up faster than it should, so things took off faster. And so a low catalyst that's usually low might not have been low on that one. The other thing is remember controls for your catalyst preparation. That is a key step in any catalyst screening. And so, there's always room for a good control because in the end, you'll feel better. You will feel more confident in your data. And finally, the statistical analysis. In order to do that, you have to have replicates. And I know I keep stressing the use of replicates. And the reason I do that is I know I get a lot of pushback from my project managers and my clients. We want to run as many catalysts on one plate as we can. It's all about time and getting data out fast. But fast data isn't always reliable data. So try to find balance between your replicates and running your unique catalyst compositions. And again, like I said, a true statistician, I think, would tell most people a 5 is the absolute minimum that you can do, but we usually do 3. So I want to just give you a couple quick examples of our plates, controls, and replicates. So on the next slide, I've highlighted 7 runs that we did this optimization experiment that we ran took us about 10 plates total. And this is how our controls kind of looked across all 7 of these plates. As you can see, there is variation. So this is where when we start comparing catalysts from like plate 4 and 5 to plate 1 and 2, we will look at how closely those numbers compare, and we may determine that those 2 catalysts, even though the catalyst on plate 1 looked better than the catalyst on plate 4, it might actually be comparable due to the fact that our controls are all a little bit lower on 4 and 5. So that's just sort of a quick example. As far as the importance of replicates on the next slide, I wanted to kind of give you an example of what we saw as differences and why they were so important. When we were doing our validation experiments, this is data from that, we found mass recovery to be a problem for us. We were using water as our solvent and running at higher temperatures. So we had basically solvent loss. And so we ran 8 replicates across all of our different controls. We ran a few supports and also a water blank. And as you can see, there was variance of 10 to 18%, so about 10 to 18% error depending on the catalyst. And the important parts of doing this validation is we found there really wasn't any trending based on the catalyst or the vial location. We were kind of hoping it'd be a vial location, like the outer vials would show more water loss than inner vials, but it was very, very random. And so we decided the triplicate run was going to be the best bet to get the most out of our plate with still allowing us to discard data below 75% if we had to. So this is sort of the importance of why you want to do your validation run like this and really check how many replicates you're going to need. So if you have questions on that, like I said, feel free to put them in, and hopefully we can discuss any of those later. So moving on to the next slide, you've got all your design done, you've got your controls in place, you've got your replicates there, and you started screening, and you're doing your analysis of all your samples, and all of a sudden you stop and go, wow, there is a lot of data here. That is probably the number one thing, not complaint, I would say, but the number one surprise that I get from most of my project managers and my clients that I'm working with, just the amount of data. So the question is, how do you look at it without going cross-eyed? The thing that I've discovered over the years is you need to start simple and then move to more complicated analysis techniques or data analysis techniques using smaller sample sets. So like I said, number one is define your analytical techniques at the beginning. And when you define these analytical techniques, you have to keep in mind that the analysis part is going to be your bottleneck. No matter what you're doing, analysis is always the slowest part of screening because you're looking at so many samples. So you want to get analytical techniques at the beginning that can limit your sample sets for later techniques. That's why we look at mass recoveries. We look at carbon distributions between gas, liquid, and solid. These are things that we can use to go, okay, that catalyst isn't very good. We're not going to look at it much in detail anymore. And then we can do more longer-term analysis techniques such as HPLC, elemental analysis, things like that. So that's number one step in keeping it simple and then becoming more detailed. As far as looking at the actual data, you can do the same thing. Look at simple trends first. You know, that's where you pull out Excel and you start just looking at the simple bar graphs and things like that, line graphs and different trending. From there, you can move on to combining the different variables, looking at the ratios between those variables and sort of see how those trends go. This is a really important step that I think people shouldn't forget, but at the same time, it's not the first thing you want to step into, because you will find things that you may have overlooked by combining a lot of these variables. But if you start with it right off the bat, you're going to get lost in these details and find that you've missed some really key, obvious things. And the last thing I'll say about analyzing your data is really try to find graphing software that helps you. There's a lot out there, and the problem is very few will do everything. Excel is good for a lot of things, but things like Origin, Kaleidograph, there's a lot of ones like that that will help you do additional things. They might be more tedious to do simple bar graphs, but they'll let you do a little bit more complex trending and stuff like that. And then when you really want to get into a lot of the statisticals, there's of course the really high-powered ones like Spotfire, Tableau, things like that. But you should try to probably use a suite of things. That's usually what I find works best because it allows you to look at a lot of different factors. So on the next slide, I just want to kind of go over on these next couple what kind of how we approached, kind of give you an example of how to start looking at your data simply and then moving to more complex analysis. So the first thing we did, like I said, is we looked at carbon distribution because catalyst coking was like a major go or no-go for our catalyst composition. If we produced a lot of solid in it, we weren't interested in that catalyst because it was going to have a really low lifetime. So what we did is just pulled out some of the simple trends and for the different catalyst composition, catalyst components, and looked at how solid formation was and how liquid carbon was as well. So if you see, these are just simple bar graphs made in Excel, and I've highlighted here in black trending from low to high levels of A, with everything else being constant. And we found really close, really quickly up front that at low loadings of A, we were producing a large amount of solid. I mean, in some cases up to about 60%. It was a terrible catalyst. So we found that component A had a huge influence on catalyst coking. We also wanted to look at component B, and that was the three bar graphs, or the three catalysts highlighted in red, and these also go from low loadings of B to higher loadings of B. And as you can see, B has the opposite trend. At very low loadings, we get not as much solid formation. So from here, you can say high loadings of A are good, low loadings of B are good. And then finally, we also looked at the amount of component C, and those are, if you compare the three catalysts highlighted in blue, again from low C to high C, this had a very more minute influence on the amount of solids production, but higher loadings seem to minimize the amount of solids produced. So that's, like I said, that's kind of an initial how I would, kind of look at the catalyst in a simplistic manner with just some really high level. We did a little bit more detailed on the next slide. Again, still looking now at solid formation, but here we were looking at just our top catalysts that didn't make a whole lot of solids. So we were looking, you can see the axes here on these graphs only go up to about 4% carbon, as opposed to, we were looking at some with about 60. And we started at this point to combine components a little bit and see if they had an influence on trending. And a lot of things that went with the more simplistic followed through with this more detailed. So some of the things I'll point out, and I won't go too much into detail with some of these, but again, we found that high loadings of C tended to decrease our solid. You can see that as we go from low to high C in both the both graphs on the left, the amount of solids is going down even at low solid producing catalysts. Low B also decreased our solid production. You can see that on the top left graph, which was again we saw earlier with the larger solid producing catalysts. And then D, we hadn't really looked at too much on the first one because, and we didn't see there's much of a trend until we started looking kind of at a combinational effect. So the on the graph at the top right, we looked at two compositions of two loadings of A, 0.5% and 1%, and then we looked at increasing amounts of component D, and I tried to keep the other components the same. And as you can see, depending on the loading of A, we got two different trends. Either at low loadings of A, the solid amount got a lot higher when you were going from low to high amounts of D. But at 1% A, when you went from low to high amounts, you were seeing a slight decrease, or at least a lot smaller change. So as you can see, we went from real simple to then starting to look at slight combinations and whatnot, but there's still bar graphs, they're still in Excel. The next slide shows kind of the next level up, I would say. This is where we took all of the data and threw it into Origin, and we wanted to look at combining or multivariable trends. And so in this case, because we had 4 different components, we needed 6 different graphs to compare each of those components to one another. And this is where things start to get complicated, and you kind of have to do another few little steps to tell yourself, okay, what am I really interested in, and how much confidence can I have in like these surface charts that I'm producing. And the thing that we always kind of came to is how much scatter is between your data. As you can see, if you look at the multivariable trend between A and B, those data points are grouped fairly close together, which gives you confidence in that surface plot that's made of an average of those data points. Whereas you go on the far bottom right chart that looks at D versus C, those data points are scattered all over the place, which means there's probably not a lot of trending in that surface chart. Doesn't really have a lot of influence. So you can do some simple things. You can also do way more complicated than this, where you start looking at mathematical statistics and really diving into the mathematics, I guess, behind statistics is what I'm trying to get at. But this was a really good first step for us, and we found A and B definitely have the strongest influence, whereas the rest of them have a more subtle influence. So to the last slide, I just want to show you, you can take looking at these multi-variable trends even more in depth. We knew that A and B had huge interactions. And so what we did is we looked at the desired products, we looked at our intermediates, we looked at anything else we couldn't identify, we looked at undesired products, and kind of added all of those up to get what you saw in the first graph, which was our amount of carbon in our liquid phase. And that kind of told us a story, because if you just look at the carbon in liquid phase, we would have said that a high loading of A and a low loading of B were definitely our best catalyst. That's the one we want to use. But if you look at the desired products and things like that, we found that actually a high loading of A and sort of a medium loading of B, or a medium loading of A and a low loading of B, was actually preferable. So you can learn a lot by kind of breaking all of the different components down and using these multivariable surface charts. It's just sort of another way. From here, like I said, you can go to ratios and a lot of different things. This is just a very small glimpse, so if you have questions on other things that you can do, like I said, I hope you write in and let me know. So just to summarize our last points, the points I've made on this last slide, number one is take your time when you're designing your experiment. We all want to start, we all want to get going, and we've all got deadlines we're trying to meet. But if you don't really take the time to design your experiment properly in the beginning, you're not going to have the data you want at the end, and you're just going to have to kind of go back again. Make sure that you validate your instruments before you start your screening. You don't want to get halfway through and realize that this isn't going to work for you or it's doing something wrong. Utilize your controls. Remember your replicate. All of those things are really important for doing your statistics and making sure you have confidence in your data. When you start looking at your data, again, start simple so you can reduce the amount of analytical time that you're spending and the amount of complexity that you're trying to make sense of. Then move to more complicated data analysis and narrow down to what you think is your top performing catalyst so that you can move forward with your larger scale testing and things like that.